Okay, I'll get started. So today we're going to finish off more examples of the primal dual method to develop good online algorithms. And then hopefully if we have time, we'll start something else, namely approximation algorithms. Okay, so I promised you last time that we're going to, again, take another look at ski rental. So cost of renting is $1. Cost of buying is $B. And I think you're scribing today, right? Is that right? Okay. And we saw deterministically you can get a two competitive algorithm online. Okay. So now I'm going to show you a randomized algorithm. The bound that I'm going to show you is originally, so today we'll get a randomized randomized algorithm with competitive ratio. Okay, so the competitive ratio is going to be roughly e over e minus 1. But to be more precise, it's going to be 1 plus 1 over 1 plus 1 over b to the b minus 1. Okay. And as b gets large, notice that when b is large, 1 plus 1 over b to the b is roughly e. Okay. So this is roughly 1 plus 1 over e minus 1, which implies that this thing is roughly e over e minus 1 as b gets large. Okay, so this thing is always at least e over e minus 1, but it converges, it goes down toward e over e minus 1. And the worst case is when b is 1. When b is 1, this will give you 2, which b is certainly at least 1. Otherwise, you would never bother renting. Okay, so this bound is due to Carlin and others. Carlin et al. Algorithmica 94. But today, I'm not going to show you the result the way that they did it. I'll show you today. You'll see a primal dual view of getting this bound. And this, so you can see this book by Bookbinder and Naur. So they introduced in 2005, I mentioned last lecture, this primal dual approach of getting good online algorithms. And then they wrote a book, I believe in either 2007 or 2009, I can't remember, that gives this as one example amongst many others. Okay, so remember the model. Okay, so we have a covering LP. And we see the constraints one at a time, and if the constraint's not satisfied when we see it, we have to make an online decision to change some of the variables to satisfy it. And the variables that, throughout time, the variables have to be monotonically non-decreasing. Okay, so let me remind you, we did this last time, what the LPs are. So for ski rental, we have the primal LP, which says minimize bx plus the sum I from 1 to k zi. Okay, so zi tells us whether we rented on the ith day, and x tells us whether we've bought the skis, and there are k days. Of course, we don't know k ahead of time. And there are the constraints. One constraint is that for all days I, we had to either have rented or bought. And also x is at least 0, and for all I, zi is at least 0. So this is a covering LP. And then we have the dual. Okay, so remember in the dual, constraints in the primal turn into variables in the dual. And the right-hand side in the primal turns into the objective function in the dual, the thing that you dot product with. So you get max sum I from 1 to k of yi. So you have one variable for every day, such that the sum I from 1 to k of yi is at most b, and also that for all I, I think 0 is less than or equal to yi is less than or equal to 1. Okay. So the way we're going to do this is we're going to online build up both the primal and dual solutions. Okay. And they're both going to be, we're going to maintain that they're both feasible. And we're going to say that the objective cost on the primal solution we find is not too much bigger than the dual. Yeah.
So is there any way to intuitively describe what the yi represent after you've done this dualization?
Let's see. Right. So for us, as we build this, yi is either going to be 0 or 1. So basically, yi is going to be 1 for the days where we rent, and then it's going to be, and then it's going to start being 0. So it signifies that you rented on that day, sort of, but not. I mean, there are no integrality constraints here, so yeah. Okay. Yeah, I mean, we will see in the next example when we do set cover, we will see that. Well, actually, not then. When we do approximation algorithms and we analyze a set cover approximation algorithm, there will be a more intuitive way of thinking about the y's. Okay. So here's going to be our algorithm. Initially, x, all zi, and yi are 0. Okay. When we see a constraint, so what are we seeing online? We're seeing these constraints online. Every day we see a new constraint, x plus zi is at least 1. So when we see constraint I online, if x is already equal to 1, do nothing. Okay. Otherwise, we're going to set zi to be 1 minus x. We're going to set x to be 1 plus 1 over b, x plus 1 over cb. C is a constant that I'm going to choose later. And we're going to set yi to be 1. Okay. So what do we need to understand? We need to understand what's the ratio between the objective functions in the primal and the dual. And we also want to ensure that x and y are both feasible, or the primal and the dual solutions are both feasible. Okay. So first off, let's bound the primal objective over the dual objective. Well, in every step of this, they either both don't change, okay, or the dual objective changes by 1. It increases by 1. And how much does the primal objective change by? So in every step, the change in the dual objective. In every step, okay, so either both objectives don't change, or the change in the dual objective exactly equals 1 because we increment yi by 1. And the change in the primal objective well, what's the change in the primal objective? It's b, so right, there's this b here. B times the change in x plus zi. Okay. And what's this? What's the change in x? Well, this is b times the new value of x is 1 plus 1 over b x plus 1 over cb. And the old value of x was just x. And this x cancels that x. So this whole thing, is x plus 1 over c. And then when you add in the zi, and then let's say this is plus zi. When you add in the zi, remember zi is 1 minus x, so this is 1 plus 1 over c. So the primal objective over the dual objective is at most 1 plus 1 over c, namely 1 plus 1 over c divided by 1. Okay, good. So now we just need to say that this thing is feasible, or that x and y are feasible. Okay, so let's look at the primal. Now, zi is just 1 minus x. So that's a tight constraint. And certainly, we never make anything negative. So the primal is seen to be feasible. Okay. How about the dual solution that we're building up? Well, definitely all the yi's are between 0 and 1. But then there's this constraint that we need to ensure happens. Okay? So primal feasibility is just immediate. And then we have dual feasibility. We need to ensure that the sum I from 1 to k of yi is at most b. Okay, well, how many times do we set yi to 1? Well, we do that as long as x is less than 1. Right? Once x is 1, we don't do this else condition. So we just need to make sure that we can only be in this else clause b times. We need to show can only have x less than 1 at most b times. Okay. So let the increment to x on the ith day be xi. In other words, I mean x is the sum over I of xi. Right, so x starts off as 0, then we add some amount x1 to x, then some amount x2 to x. So it's not hard to convince yourself from this formula that, first of all, x1 is 1 over cb, and the xi are geometric with ratio q being 1 plus 1 over b. This implies that the sum from the first day to, say, the b minus first day of xi is equal to 1 over cb times the sum I going from, to the bth day, I guess. I going from, let's say j going from 0 to b minus 1 of q to the j. Okay. And this is equal to 1 over cb times, what's q? 1 plus 1 over b to the b minus 1 over q minus 1, which is 1 over b. B's cancel. That b cancels that b. And this is equal to 1 plus 1 over b to the b minus 1 over c. Okay. And what did I want? What did I want? I wanted that after b days, x is going to be 1. So now I'll choose c. So set c equals 1 plus 1 over b to the b minus 1. Okay. So that's it. We have a 1 plus 1 over c competitive ratio. And c is this, which is exactly what I promised you. And now x and y are both feasible. And what's the point? The point, remember, is that in general, you have that any dual solution, so let's say cost of the dual is always at most, let me call that cost of d for dual, is always at most opt of the primal, is always at most cost of the primal, where these are feasible solutions. So cost of the primal, I mean for any feasible solution. Okay? And we just said that the cost of the primal is at most 1 plus 1 over c cost of the dual. Right? So now you can bring this opt over here. This implies that the cost of the primal solution we found is at most 1 plus 1 over c times opt of the primal. So we're 1 plus 1 over c competitive. OK. So are we done? Do I now have a 1 plus 1 over c competitive algorithm for ski rental? It's not integral. The ski rental problem says every day, I mean, what does this mean? Like every day I'm buying some fraction of the skis and I'm renting some fraction of the skis. That's not actually a valid ski rental solution. Okay. And as and I haven't used randomness anywhere. I told you I'm going to give you a randomized algorithm. Okay. So how are we going to actually get a valid integral randomized solution? Well, this is the ratio I want. So as you might imagine, what I'm going to do in my randomized algorithm is somehow get this in expectation. Okay. So problem, we can't fractionally rent or buy on each day. We must be integral. So the fix is going to be using randomization. And how do we do that? So the randomized algorithm, okay, the randomized algorithm that I'm going to tell you is going to actually maintain that, okay, in its memory. But it's going to do something first. So the first thing it's going to do is initialize all of x, zi, and yi to 0 as before. But it's also going to pick at the very beginning just a random number uniformly at random. Okay. And when seeing new constraints, we will update the x and zi and yi as before, fractionally. Okay. But now we need to choose, are we going to actually rent or buy? So we have these fractional solutions lying around. Do we rent or buy? We buy. So here's going to be the picture. When do we decide to buy? So I think it's easier to just draw it. So here's the interval from 0 to 1. We picked a random alpha. Alpha, happened to be here, let's say. And x, remember I defined these xi's, these increments that happen. So, no, this is not chalk. Okay. So first we increment x by some amount x1. Then we increment by some other amount. Well, this is x1 here. Then we increment by some other amount x2. Then x3. Then x4. Remember, and x is just the sum of the xi's. When do we buy? We buy on the day that alpha landed in. Okay. So here, we'll buy on day 4. Okay, so now let's analyze our expected cost of doing this. The expectation of the cost. Well, the cost is just the sum of money you spent buying and the money you spent renting. So that's the expectation of money spent buying plus the expectation of money spent renting. Okay. So this thing here, so now the expectation of the money I spent buying that's just equal to b times the probability that I buy. And what's the probability that I buy? Well, let's say x is the sum of the xi, so x is right here. So the probability that I buy is the probability that alpha is less than or equal to x, which is exactly x. Okay. And what's the expectation of the money spent renting? Well, that's by linearity of expectation. That's the sum over all I of the probability. Well, you can define an indicator random variable for whether or not you rented on day I. And then the total number of days you rented is just the sum of those indicator random variables. Okay. And the expectation of one of those indicator random variables is just the probability that you bought. So this is the sum over I of the probability that, or rented, sorry, the probability that you rented on day I. What's the probability that you rented on day I? Well, alpha has to be less than x1, x2, x1 plus x2 plus dot 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 up to xi minus 1. Okay, so this is equal to the sum over I. Sorry. So if alpha is less than that, it means you buy, you don't rent. So alpha has to not be less than that. So it's 1 minus that. So 1 minus x1 plus x2 plus dot 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 plus xi minus 1. But this is just what x was at that point in time. So this is 1 minus x at that point in time, which is exactly zi. So what do you know? Our expected cost is b times x plus the sum of the zi, which is exactly, did I erase it? Which is exactly the primal objective. So in expectation, we achieve the primal objective. Okay. So now we actually do have our close to e over e minus 1 competitive algorithm. Okay. Questions about that algorithm?
So the day is chosen in advance.
Yeah. Yeah, that's right. Because the way we update x, right? I mean, the way that these xi's are deterministically defined. So once we pick alpha in the beginning, we know when we're going to buy. That's right. Any other questions? You look like, do you have a question or no?
Yeah, it's just why is it xi? Why do we go all the way to xi? So why is it all the way to xi?
Should it be xi?
That means that we're greater than the sum.
If we rent it on day I, so let's say the probability of renting on day I is 1 minus the probability of buying on day I. So what's the probability that we buy on day I? Well, at the beginning of day I, we haven't done the increment to x yet. Yeah. So for example, think of day 1. Day 1, x, at the beginning of day 1, x is still 0. And then we add the increment in the else. And then else. But certainly, even if I somehow m off by 1, if you added an xi here, that would only help you, because then you'd be at most zi. So, okay. Good. Okay, so I want to show you one more example of a primal dual online algorithm. Okay. So here I want to look at set cover. And the algorithm, the bound that I'm going to show you is due to a lone our book Zar, Bookbinder, and Naor. This is COMP 09. Okay. So let me refresh everyone's memory and introduce some notation for set cover. We have a universe. So the problem definition. So we have a universe of elements one up to n. And we have m sets, S1 up to Sm. Each one is a subset of the universe. And our goal, and let's also, our goal here, okay, let me write this out. Our goal, pick subcollection of the SI covering the universe. Okay. Their union should cover the universe. So, any questions about the problem definition? So I haven't said anything about online, but this is what I mean by set cover. So what's online about this? What's online is that, so we know that there are these m sets. In the beginning, we know there are m sets, S1 up to Sm, but we don't know anything about what they contain. Okay? And online, we see elements. And when we see an element, so the person will tell us which sets contain this element. And now we have to, if we haven't already picked one of those sets into our set cover, then we need to choose a set right there and then to cover it. Okay, so we see elements online and must immediately cover them. Okay, so that's online set cover. Who has seen set cover at some point in their lives? Who has not seen set cover at some point? Okay. So, okay, who has not seen NP hardness, the notion of NP hardness? Okay, people have seen NP hardness, good. So set cover is an NP hard problem, meaning that unless there's some huge breakthrough in computer science, we don't expect to have a polynomial time algorithm. Okay, so for that reason, I claim that at least if our online algorithm is efficient, we're not going to hope to get. Oh, and furthermore, okay, not only is it NP hard to solve set cover exactly, but it's even hard to approximate. Meaning that if I give you the entire set system in the beginning, there's no online here, it's an offline problem, and I say, find me the best set cover, it's hard to find a set cover that's better than a log n approximation of the optimal set cover. Okay.
By optimal, you mean what's smallest?
Small, yeah. So you want to find some set cover that's not worse than alpha times the best in terms of size of subcollection. So beating alpha being log n is a hard problem. Yeah.
Number of sets or size of the individual sets?
Log n approximation.
So number of sets though. Like if you have.
Oh yeah. What do you mean?
Well, I mean, you could like say you have two sets which are both missing one. That's better than like having a bunch of large sets that are disjoint.
If you have two sets that are
I'm just asking what the optimality condition is, right?
Okay, so you must cover all the elements. That's a requirement.
You could optimize either for fewest number of sets or little overlap.
Fewest number of sets.
Yeah. Okay. So that was my question.
Yeah. Oh right. And I guess I didn't say that. Minimize number of sets taken in your subcollection. Okay, so if we're efficient online, we don't expect to do better than a log n competitive ratio. Otherwise we would have a better offline. Just pretend that the things came online, even though you know everything. Okay, so we'll show online log n times log m competitive ratio. Okay. First, I'll show you. I think in both cases the algorithm will actually be the same, but first I'll show you a purely primal view. And we can prove correctness just for this primal view, but then I'll show you a primal dual view as well. Okay. Okay, good. So let's write an LP relaxation for the set cover problem. So primal. So we're going to have one variable for every set. So let me just write this M set. So we have a collection C of sets, which is S1 up to Sm, where Si is a subset of 1 to n. Okay, so the primal, we're going to have one variable for every set, and we want to minimize the number of sets taken. So we want to minimize the sum over S in our collection of X sub S. And normally XS has to be either 0 or 1, but we can't enforce integrality in linear programming. If you enforce integrality, that becomes integer programming, which is NP hard. Okay, you can encode, for example, 3set as an integer program. So what are the constraints? So for every I in n, we have a constraint that says that the sum over S containing I of XS has to be at least 1. And furthermore, X coordinate-wise has to be non-negative. You could say, we could also have a constraint saying X has to be at most 1, but that's not necessary because no optimal solution would make any Xi bigger than 1. Okay, that's the primal. There's the dual. Remember, we have one variable for every constraint, so we have one variable for every I. So this is maximize the sum over I from 1 to n of yi. And for every variable, we have a constraint. So for all sets S in the collection, we have a constraint which says that the sum over I in S of yi is at most 1. And we also have the constraint that y is at least 0. And yeah. Okay. Well, this doesn't matter. So the at most one, again, doesn't matter so much because this already sort of enforces that. OK, good. So just out of curiosity, who here has not seen any differential equations ever? Oh, OK, good. So yeah, maybe you thought, maybe when you learned differential equations, you thought, why would I never use diffie-q's? I'm going into field X, which where that doesn't appear. So we're going to use diffie-q's. Okay, so but not anything too fancy. You'll see in a second. So what are we going to do? We're going to maintain, as usual, primal. We're going to maintain primal and dual solutions, and we're going to show that we can get feasible solutions for both, where the objectives are not far off from each other. Okay, that's the usual game. So the algorithm. Remember, we know the thing that's coming online are the elements, okay, not the sets. We know the set, so we're going to we know that there are m of them. Initialize x to be 1 over m everywhere. And now what comes online? One of these constraints comes online. An I comes in. Okay. And I might not be covered. Okay. So if I is not covered, so meaning this constraint is not satisfied. So right now I'm not going to show you, I wrote the dual up there, but I'm going to show you a purely primal way of looking at things before I go move to the primal dual. We're not going to maintain anything about y right now. Okay, we'll just work in the primal. What I'm going to do is, so when we see constraint I, okay, while suppose I is in some sets, SI1 up to SIK, or SIR or something. I don't want to use I twice. SJ1 up to SJR. Okay. So if this constraint is already satisfied, we're done. If it's not satisfied, while constraint is not satisfied, we'll run a continuous process where XS changes according to over time. Imagine that there is some time unit. And the way that we vary XS with time is that dXS of t dt is XS of t. Okay? So run this process simultaneously for all of these s's, sj1 up to sjr, until the constraint becomes tight, or until the constraint is satisfied. Okay. So the solution to this, I mean, we're not doing any fancy diffq-qs. The solution to this differential equation is just e to the t. Okay, after t time steps, you become e to the t. So after xs evolves for t time steps, it multiplicatively increases by e to the t factor. So okay, I could have just said multiply all of these by e to the t for the smallest t, which satisfies the constraint. But there are some fancier examples of covering LPs where well, first of all, I mean, this time thing is you'll see in the analysis, this view of things running for continuous time is gonna, help us understand what's happening. Okay, so now, definitely the primal solution we end up with, I haven't said anything about the dual, the primal solution we end up with at the end of everything is feasible, right? Because we run this for time until it's actually satisfied. So everything is satisfied, and everything ever becomes negative. The question is just, how can we argue that our competitive ratio is not that bad? Okay. So I want to compare to opt somehow. So this constraint is not satisfied. But opt is satisfying this constraint, right? So in particular, and which sets are we incrementing? We're incrementing the excesses which contain I. One of those has to be in opt's solution, right? So every time we run this continuous time process, we're evolving someone who's in opt. Whenever we run this evolution, some set in opt is increasing. Now, if you focus on one particular set in opt, how many seconds can it, or time steps can it evolve? In this process, right? So all the excesses start at 1 over m, and we would never bother evolving anything unless a constraint was not satisfied, right? So the fact that the constraint is satisfied, maybe I should also say this. So if a constraint is not satisfied, right, it means that set in opt is less than 1. Okay, so how many time steps can any set in opt be evolved for? Natural log of m. No set in opt evolves for longer than ln m seconds, right? So the total number of seconds that were ever in this evolution phase is at most opt times ln m. Like over the entire course of the algorithm. So the algorithm runs this process for at most opt times ln m seconds. Okay, that's all nice. But what is the amount of time that we run have anything to do with being good compared to opt? Well, what's the derivative of the primal objective as a function of time with respect to time? Okay. So the only part of the primal object, so this is equal to the derivative of x sj1 plus x sjr dt, right? Because the other variables aren't changing. What do I know about this sum during the evolution? I'm evolving because the constraint is not satisfied, right? So what does that mean? Yeah, it's at most 1. This sum is at most 1, right? So so the derivative of this with respect to time is exactly, according to our differential equation, it's exactly sxj1 of t plus dot 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 plus xsjr of t. But this is at most 1. It's less than 1. Otherwise, we wouldn't have bothered evolving. Okay. Now, the objective starts off at 1, right? It starts off, so x starts off as 1 over m everywhere. So our primal objective starts off as 1. And the way that it changes over time is every time unit, it increments by at most 1. It increments by at most 1 in every time unit, and it only runs for opt times ln m time units. So that implies at the end of the algorithm, the primal objective is at most opt times ln m. Okay. So we have a ln m, we're ln m competitive. Or are we? Again, it's not integral. Okay, so yes. But
Match the competitive ratio that you said we were going to get.
yeah, it's better. Yeah.
It's a lot better.
Yeah. In fact, I should say that in that paper, they show that not only can you achieve this, but you cannot achieve better by more than log factors. So that's up to log. That's basically the right answer. Yeah. So I guess if you're looking for final projects, you can investigate this removal of a log. I think there's a gap of log, but yeah. Okay. So again, we have the same problem. This is not an integral solution. We have to, at every time step, we have to actually take some set. Right? One of the x's has to actually be set to 1. We can't just keep them as fractions. So before I fix that, I want to give a primal dual view. Actually, I should investigate. I should check that paper more carefully. This paper came out. The conference version came out before. It came out in 2003, which is before Buchbinder and Naor did the whole primal dual view of online algorithms. So I didn't actually read the paper, but I think they only did this primal view of things. They didn't do the primal dual view, I think. I mean, otherwise the time doesn't make sense. So let me show you the primal dual view. So this is all the purely primal view. We never talked about the dual. So how about the primal dual view? Okay, so we'll maintain the excesses as before. Okay. but we also want to maintain y's. So y is initially set to 0. And as we run evolution to satisfy the ith constraint, we also evolve yi according to the differential equation dyi of t dt is 1. In other words, every second, yi goes up by 1. Okay. So already we see that the primal objective in every time step is going up by at most 1. The dual objective, right? The dual objective is just the sum of the yi's. The dual objective in every time step is going up by exactly 1. This already tells us that at the end of the day, when we get our x's and y's, our primal and dual solutions, the cost of x is at most the cost of y. The primal cost of x is at most the primal cost of y. Okay. Now, that tells something is a little off, it sounds like, right? Because if the primal is feasible and the dual were feasible, and the primal is at most the dual, well, we know that the dual is always at most the primal. That would just say primal equals dual, which says we got the optimal thing. So the catch is that this dual is not going to be feasible. But what we're going to show is that if we scale the dual down by log m, roughly, then it would be feasible. Okay, and that's going to be good enough. So x, just like before, is feasible. We already talked about that. X is feasible. So a claim is that if you take y and entry-wise, you just divide by log m, that's dual feasible. Feasible for the dual program. Okay, proof. I mean, basically, what does that mean? We need to show that for all s in the collection, the sum over I and s of yi is at most ln m. I mean, we need to show that this constraint is only unsatisfied by a ln m factor. Right? Then that would give it to us. Well, why is that the case? Well, let's focus on a particular set S. Okay. Now, look at this sum. If some yi is being increased in this sum, we're also simultaneously increasing xs for every s that contains I. So whenever this sum is increasing, we know that xs is increasing. But we already talked about this. How long can xs possibly increase? Ln m seconds, right? Because then it becomes 1, and then we would never run the evolution again. So that's it. Whenever sum of yi, I and s increases, we know xs is increasing. And this is increasing at a rate of exactly 1 at every time step. So after ln m time steps, this is exactly ln m. We know xs is increasing. And xs can only increase at most ln m time steps. So that implies that sum over I and s, yi, is at most ln m. So if you divide by ln m, it's feasible. So what we just showed that, again, the cost of yi, the cost of y over ln m is at most, the dual cost is at most opt of the primal, is at most the cost of the primal on x, and which we know is at most the cost in the dual of y. Right? And this cost is linear, so this is just 1 over ln m times the cost of y. Right, so that implies exactly what we want. That implies that, just bring this opt over here. That implies that the primal cost of this x that we found is at most ln m times opt. OK, great. So, I mean, we didn't do anything different. We didn't get anything new. We just saw a primal dual way of looking at it. In the purely primal way, we compared directly with opt. In the primal dual way, we never really talked about what opt was. We just built a dual solution. OK, so now let's talk about actually fixing this thing. So kind of the first attempt is, so first let me write, getting an integral solution. So the first attempt would just be, at the very beginning, for each s in the collection, pick uniformly random alpha sub s in 0 to 1. Once x sub s is bigger than alpha s, so maintain the fractional solution just like we were doing. Once that fractional solution on s is bigger than alpha sub s, take it into the collection. Take s into our solution. Just to be clear, that doesn't mean we set xs to 1. Okay? We're going to keep the fractional solution running just as it ran before. Just on the side, we're going to maintain the sets that we're actually going to output. Okay? So when we decide to take s into the solution, that means we're going to output s as being one of our sets, but we're still keeping x sub s the fraction that it was before. Okay, so that we can still say that our fractional solution is giving the same cost as it was before. Okay, so one thing you can show, which is basically the same thing we did last time, is that the expected cost of this integral solution is the cost of the fractional solution. Okay. I'm not going to do that computation, but it's roughly the same as what we did before with ski rental. But there's a problem. What's the problem? Huh? Might not be feasible. Exactly. Okay. At least with ski rental, if we didn't randomly decide to buy, we were always renting anyway, so we were always feasible. Here, if we mess up and we don't actually take it into the solution, then that element's not covered, and this might not be feasible. in their request sequence. And so what's the fix? So for this fix, I'm going to, I'll assume that you at least know n. All right. You can actually remove this assumption. Maybe I'll put it as a homework thing, I don't know. Or maybe I'll put it in the notes. But let's say you know n, you just don't know what's contained in what. So the fix is, so what's really going on here? So we know from the primal feasibility that, so view xs as now being the probability that we actually put s into our solution, right? So this sum is like, view it as the amount the point I is covered, the number of times I is covered. What this is saying is that the expected number of times I is covered should be at least 1. Okay? But if you randomly put things into the set with this probability, then there's unfortunately some good chance that you won't actually cover it. So the trick is just to boost it. So rather than have it be that the expected number of times we cover the element is 1, make the expected number of times we cover the element log n. Okay, so the fix is once xs is bigger than or equal to alpha s over some big constant times log n, then take s into the solution. You look troubled. Are you troubled? No?
There's still some probability that we won't satisfy.
Yeah, there is.
Okay.
This is going to be small. Okay. Wait, is that really what I want to do? No. Sorry, this is not what I want to do. It's a good thing you're troubled. You should have been troubled. Yeah, I sensed. Okay, so this is the actual fix. For each s, we will pick alpha s1, alpha s2, up to alpha s r in 0, 1 uniformly at random, and also independently. And also r will be, some big constant times ln n. Okay, and then if xs is bigger than or equal to alpha s j for any j, then put s into our solution. Okay. Good. So now our expected cost increases by at most an r factor, which is why we get, I don't know if I erased it, which is why we get a log n times log m competitive ratio, an r times log m competitive ratio. And if you look at any element, the probability that its constraint is not satisfied for any one of them, let's say that the probability that its constraint is not satisfied due to alpha s1 is at most some constant, a half or something. So the probability that none of them satisfied it is exponentially small in r, which is 1 over poly n. So by a union bound, they'll all be satisfied. There are only n of them, right? So if the failure probability is 1 over poly n, then by union bound, our failure probability of not being feasible is 1 over poly n. So that's it. Yeah.
Seems like we could do something that like wouldn't fail at all by just like for each n.
Yeah.
A random thing from 0 to 1, and like subtracting out the
Wait, say it again.
because it seems like for each n, right, the probabilities are gonna like add up to 1, but they don't. You can't. It doesn't work because you're not like sampling correctly. So if you sample something from like 0 to 1, that will correspond with like one of the things, and you'll choose like that one. I don't know if that makes sense.
Okay, so one thing that's worrying about me about this like deterministic rounding without. So I mean, are you going to lose a log n in what you're doing?
I don't know.
Okay, so one thing about set cover is like for the offline problem. One way to get a good algorithm for set cover is, did I erase the primal already? Maybe I erased the primal. You solve the primal, that gives you probabilities for each set, and then you round up. Then you take the set with probability equal to x of s. Okay, that gives you a randomized algorithm for set cover. And you run into the same issue that it might not be feasible, so you blow things up by this log n. Okay, so for set cover, we know there's a proof that you cannot beat a log n approximation unless unless p equals np. Okay, so so that's why I'm a little cautious about deterministic rounding, which doesn't lose anything. Okay, so I have about 10 minutes left. I guess I'll set things up for next time. So we're done with primal dual online algorithms, and I want to move into a new but related topic. So the next topic is approximation algorithms. So what's that all about? So the basic gist of things is we have some optimization problem. We want to minimize or maximize something, for example, set cover. Okay. And now we're not online anymore. This is all offline, okay? So we're all offline now. And the best known algorithm for solving this optimization problem is slow. Okay, so maybe the problem is NP hard, and the best algorithms we have are exponential time. Or maybe we do have a polynomial time algorithm, but it runs in time n to the 10th or something. Okay, so the best known algorithms are slow. So maybe the problem is NP hard. Okay, so and that's actually this is the one we're going to focus the most on, approximation algorithms for NP hard problems. And we would like to give a fast algorithm, or at least not as slow as the one as this exact algorithm, which gets a cost that's guaranteed to be within some small factor of the best cost. Okay, so we want an algorithm, a fast algorithm, I should say, a fast algorithm, which produces solution with cost at most, let's say, some alpha times opt, where alpha is hopefully small. This is for a minimization problem. If our optimization problem is a maximization problem, then we would like to find a solution that has a value at least alpha times opt, where alpha is less than 1. At least half of opt or something. And so since we were just doing primal dual with online algorithms, I'll start off with an example here of using the primal dual method to get good approximation algorithms. So we're not online anymore, we're offline, but we can still use the method. And in fact, the primal dual method for approximation algorithms is much older than the primal dual method for online algorithms. At least the thing I'm going to show you now is from the 70s. So if you want to see more about approximation algorithms, I mean, you can see this book. There's a book on approximation algorithms by Vijay Vazirani. It's called Approximation Algorithms. So this class is a kind of a broad advanced algorithms class. I'm not going to. There are classes that exist in the world where all they do in the entire semester is approximation algorithms. Okay, but as you've already seen, that's not going to happen here. But I will talk a little bit about it. Okay, so let's look back at set cover. Okay, so now we know all the sets, we know the universe, we know which sets contain what elements. We just need to get the smallest subcollection of sets. And I'll even give them costs. So set S has some cost. CS want to minimize the sum over S chosen of C sub S while covering the whole universe. So before, C sub S's were all 1. Okay, so let me look at this primal dual approach. So I think, so for people who took CS 124 with me, and I think even when Professor Mitzenmacher taught it, I think he did set cover. If the CSs are all 1, there's this greedy algorithm. I mean, you can run the greedy algorithm for other CSs, where at every step, as long as there is an element that hasn't been covered yet, you choose the set which covers the most uncovered elements so far. Okay, so there's a corresponding greedy algorithm, which I'll tell you very soon, for the one with costs. But so what's the primal? The primal is minimize the sum over all sets S of CS times XS. XS tells us whether or not we took the set, subject to the constraint that for all I in the universe, the sum of X of S for S containing I is at least 1, and X is at least 0 everywhere. And the dual, we have a variable for every constraint. So max the sum over I from 1 to n of y sub I, such that for all sets in the collection, the sum of I in that set of y sub I is at most the cost. And also, y is non-negative everywhere. Okay, so what's the greedy algorithm? As long as there exists an uncovered element we will put S into our solution such that S minimizes the ratio between its cost versus the number of elements that it covers, the number of new elements S covers. Right. So this is exactly the generalization of the greedy algorithm when the costs are 1. So let's do, I think I have time to actually do the analysis of this because it's very short. So let's do a primal dual analysis. So initially, x and y are equal to 0. When we take some set S, that means we set xs to be 1. And we're also going to set and also for each newly covered I in S, we'll set yi to be the cost of S over the number of newly covered elements at this point. Okay, so when we take a set S, we set xs to be 1, which means we just increased the primal objective by the cost of S. And for all the newly covered i's, we set yi. We basically make the yi share this cost. So for each newly covered element, we set its yi to be the cost of S over the number of them, which means they share it, which means that the primal and dual costs are exactly the same in these solutions we're building. Okay, so the primal and dual costs are equal. Now the primal is obviously feasible, but the dual will not be feasible. Okay, we're going to see that next time. This dual, the dual constraint is that this sum has to be at most CS. But just as before, we're going to every one of these constraints is going to violate this by at most a certain multiplicative factor, which is going to be log n, by the way. So therefore, when we scale down, we will get a feasible solution, and that will tell us that this greedy algorithm is a log n approximation. Okay. So by the way, this approach of violating the dual feasibility and then scaling down, okay, that's called dual fitting. Maybe if you want to know, a name to Google in your future, this is called dual fitting. This art of violating feasibility and scaling down. Okay, so that's it. Remember, PSET 3 is due, I think, Monday night.